Yes, 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 yes. All right. So let's jump into it. This is joint work with my dear colleague Asta. We are both employees of the Danish state. We are both in Copenhagen, but we are at different universities. Yes. So this talk is really about a fantastic theorem called the model existence theorem, and it exists in many varieties. And just to get you started on a kind of straightforward one, I show you here model existence for natural deduction for first order logic. Okay, so the idea is that we have first order logic. So here are some of its rules, right? You can see some of the rules here. To prove a conjunction, you prove the two conjuncts, right? Famous rule. And then we can from that we can define consistency, right? So what does it mean for a set of formulas to be consistent? It means that you cannot derive a contradiction from that set, right? So so this is consistency, right? You cannot from the set derive a contradiction. And then what the model existence theorem says is that any consistent set has a model. That's it, right? If you if you somehow manage to build a set of formulas that's consistent, then it has a model. And I think that's pretty fantastic in and of itself, right? Because okay, now we know consistent sets, they actually describe something, right? That's pretty nice. But if you think that's not so interesting, then maybe you like this little consequence that follows from model existence, namely completeness, right? So valid formulas are provable. That's fantastic. So if you sit and wonder, oh man, I'm so good at proving things, I manage every time, and you think, how can I be so good at it? Well, one of the reasons is that there is a proof, and that's what completeness tells you. Yes. Oh yeah. Okay. And then this is also a little bit important when we think of sets of formulas, then we think of them as in a conjunctive way, right? So M models the set of formulas. Gamma means that it models every formula in its set. So gamma is kind of a big conjunction. You can think of it like that. And you can formalize model existence for natural deductions and other proof systems for first order logic. This has been done many times. You do a deep embedding of the syntax of first order logic, and one that's very related to this talk is by Stefan Berghofer in 2007, because he built his work on the same book that we are inspired by. There are other fantastic results in this direction, right? And some of the superstars in developing these are in this room, right? And Sophie, you also showed something something earlier in the week that was really fantastic. Yeah, good. So you can also prove model existence for other logics than first order logic, and then the idea of this talk is to provide a framework for these kinds of proofs. So a framework that's fairly general, meaning that you will not only be able to apply it to first order logic, but also to all sorts of other cool logics. So the way that I will explain this to you is that I will show a concrete model existence proof for natural deduction and first order logic, following Melvin Fitting's textbook. Then I will show you our generalization of his proof, and then I will show you some instances. So show that the generalization actually applies to some logics. Yes, and actually we will start already with a generalization. So Smuljan, he invented the uniform notation, and this already generalizes a little bit from concrete first order logic syntax, because you can always have this discussion: what exact operators do you want in in your first order logic, do you want conjunction? Do you want implication? Do you want disjunction? So you know which which symbols do you introduce and which symbols do you consider derived? And then Smulian's trick is to characterize the different operators. So for instance, he introduces the kind of operator called the alpha, and the idea of those are that these act like conjunctions. A conjunction, for instance, acts like a conjunction, right? When is it true? When the left conjunct is true and the right conjunct is true, right? So therefore, we think of the subformulas of the conjunct as, well, the subformulas. But actually, right, a negated implication actually also acts conjunctively. Because when is a negated implication true? It's true when we can make the assumption true and the conclusion false. So here we will, this is maybe a little bit funny, but we will think of the subformulas being the conclusion, no, sorry, the assumption and the negated conclusion. In a similar way, you can characterize the operators that act disjunctively. So those are called beta. And then we have gamma for universal quantification and delta for existence. And you can, yeah. So let's look at the universal quantification here. So when we write gamma t, that means the instance of this universal quantification where x has been replaced with t. That's the idea. So in brief, this is the little table. Alpha, think of it as conjunction. Beta, think of it as disjunction. Gamma, universal quantification. And delta is existential quantification. Good. So this is how to prove model existence. Or rather, this is the idea. There are some details that are crucial, but I skipped to make this talk so that you can catch the airplanes, right? So the idea is that you take the consistent set you have, and then you extend it to what's called a maximal consistent set. And then it turns out that such sets are Hintzige sets. Hintzige sets have models, and the model that this Hintzige set has is also a model of your original set of formulas. So this is the idea. And of course, when you see this, immediately I think there are many questions, right? So here are some obvious questions that I'm sure all of, well, okay, those who didn't study these things are asking themselves, right? What is a Hintzige set? Why do they have models? What's a maximal consistence set? Why are these Hintzige? And how can we do the extension? So let's look at Hintzige set first. What are they and why do they have models? So so here is the definition of being a Hintzige set. So a set S is Hintzige when it has all these properties. You know, the set does not contain a contradiction, right? It doesn't contain both atomic formula and its negation, so it doesn't contain atomic contradictions. It also doesn't contain falsity or negated truth. Then let's look at the alpha rule. Maybe that's pretty straightforward. If it has an alpha, if it has a conjunction, then it also includes the two conjuncts. This is the idea. This is the definition. And then there is a lemma called Hintzige's lemma that say these kind of sets they have models. And I have attempted to put a brief and vague explanation of why this is true down here. Maybe we don't have to dwell so much on it. The point is that these conditions on a set of formulas are sufficient for it to be to have a model. Good. Okay. So that were these two questions. What's a maximal consistent set? That's the next question, right? That one with the line under. So we define the set of all consistent sets here in natural deduction. Yeah. So, you know, if S is a member of C and D, that means S is consistent relative to natural deduction. Yeah, and then what does it mean to be a maximal consistent set? Well, a maximal consistent set S is consistent and maximal. So what maximal means is that imagine there is some other consistent set that is larger than S. Well, then that set really is S, right? It's maximal in this set. You cannot find something bigger. Yeah, good. Then these maximal consistent sets, they are also Hintzige. And then the question is here is why are they Hintzige, right? What is the reason for that? So in order to realize the truth of this claim, we rely on some lemmas about how consistency works for natural deduction. So let's take a look. So for any consistent set, we know that it does not contain. This will look familiar to you, right? It will not contain an atom or its negation. It will not contain an explicit contradiction. And then here are some more lemmas that they all say something like if a certain set is consistent, then some slightly bigger set is also consistent. I think the easiest to understand is again the alpha rule. So if a set contains, if a consistent set contains a conjunction, then if you add the two conjuncts into it, then you still have a consistent set. Okay, I think you can imagine that, right? Like if you have a consistent set and you add the two conjuncts in, it's not like you can possibly suddenly out of the blue derive a contradiction, right? Because if you were able to do that, you would already have been able to use the conjunction to do the same. Yeah. Then maybe you also notice this really looks like the definition of Hintzige, right? They are very similar. So let's put them up against each other. So over here we have the definition of being Hintzige, right? A set is Hintzige if it has all these properties. Okay, so let's say that we pick some set that's maximal consistent, right? And let's look at the alpha rule. So let's say that S is maximal and it contains a conjunction, right? Then we could make it bigger. You can see here by adding the two conjuncts in. But if S is maximal, then you know we are not supposed to be able to make it bigger. So that means that the two conjuncts, alpha 1 and alpha 2, they must have already been in S. And that is what the requirement is for Hintzige set, that if alpha is in S, then so are alpha 1 and alpha 2, the two conjuncts. Yeah. I don't know. Does it make a little bit sense? There's some cautious nodding, and some people look a bit confused. Some people are nodding. That's good enough for me. All right. Good. And then the last thing, how can we extend a set S to a maximal consistent set? So this one I will really hand wave actually. So the idea is that if you have a consistent set, then take it, enumerate through all formulas, and add those in that do not introduce an inconsistency. Yeah, that's how you can do that. And this is very simplified. I'm really skipping some stuff here, so be warned about that. But this is the idea. This is what you can do. Okay, so there was a lot of information. What was important here, right? Everything was important. But I will say for our framework, the important parts are these. Okay, so if you have a maximal consistent set, then it is Hintika. That is the important idea, the really important idea here. The really important question to answer was, why are maximal consistent sets also Hintika? Right, so this slide is really important. Yeah. Good, fantastic. we have seen model existence for natural deduction. But actually those important properties, so those properties here that ensured we had the Hintika properties, those do not only hold for natural deduction, they also hold for some other things. So if we in the definition of these properties replace natural deduction consistency with axiomatic system consistency, then everything works out. And then we can get a model existence theorem for axiomatic systems. You can also put in something more funky. You can put in the set of all sets of formulas where their subsets are, where their finite subsets are satisfiable. Then you can get a compactness theorem. And by defining some other sets, you can get Leeuwenheim's golem and Craig's interpolation theorem. So whenever your set behaves like this, then you can get models out of it. Whenever it behaves like that, you can get models out of it. So let's pack all that stuff here. Let's pack it all into a definition. Where was it? Yeah, this definition. So now we say a set C is a consistency property if it has the properties here, right? So kind of informally, you can say a set is a consistency property if it behaves the same as consistency for natural deduction, but it doesn't have to behave exactly the same. It just has to do the things here. So whenever is an alpha is a member of a consistent set, then so must the same set with the two conjuncts added in B. Yeah, good. Then we can get to the abstract model existence theorem, which says if you have a consistency property and a member, then it has a model. Yeah, that's it. So let's talk a little bit about this. So does this idea work for other logics than first order logic? Yes, this has been done by other people. Are the applications of the idea similar enough that we can make a general framework? Yes. In this paper, we made a general framework. Can we express the framework with Isabelle HOL locales? Yes, we do that. And lastly, can we apply the framework? Yes, we have applied it to three logics. And I will say that the main idea of the framework is that we can kind of slice this slide into kinds. So here is a slice, or rather here is a kind. This is the conflict kind. Here's another kind, the band kind, double negation kind, alpha kind, beta kind, gamma kind, delta kind. Yeah, there's some details with delta that I will skip. So the framework has a data type for kinds, right? So yeah, there's a constructor with with two components here, and let me show you what these two components correspond to. They correspond to one of these important properties and part of the definition of being Hintika. So for instance, for the alpha kind, the idea is that this requirement on being consistent, that can be the predicate expressing that can be put in here. And then this part of the definition of being Hintika can be put in the other component. And that's one more constructor for existential formulas. Let's not spend time on that. That we also have a locale for kinds because yeah, not all kinds are meaningful. So for a kind really to be meaningful, it needs to have this property stating that any consistency property that satisfies the kind a member of that is maximal can satisfy the Hinziker part of the kind. Yeah. So the idea is really that this assumption Hinziker, it says that the important property here will ensure this part of being Hinziker on maximality. But here we are talking about only one kind. So before we were looking at that big slide with all the lemmas about being consistent and all the parts of being Hinziker, but here we have really made it local. We are only talking about one single kind at a time here. Yeah, and there are some more requirements here. They're used for the maximal consistent set construction. They are really reasonable, but I cannot explain them in 5 minutes. Okay. So maybe you think, that's a little bit annoying. We have to prove this thing and those things. But the good thing is no, you don't have to do that necessarily, because if you because we have actually done a lot of that work. We have defined locales for alpha, beta, gamma, and delta, and then shown they specialize the consistency kind locale. Yeah, you can see it here. So the idea is right here are 3 kinds, 1, 2, 3, and then we pack in the conditions and the Hinziker conditions. Yeah. Good. Okay, so we had this locale, okay, and it described a single kind, so a single of these pink slices I show you, right? But we had many pink slices. We didn't only have one, so therefore we also have a locale that combines them all. So it looks like this, and what you can notice here, it has a list of kinds. So this corresponds to putting all the pink slices into one. Into one list. And then we have an assumption, namely that indeed all the kinds in the list are consistency kinds. And here's our main theorem, namely that if C is a consistency property and S is a member, then we can extend S to a new set, and that set will have all the Hinziker properties. So this really says maximal consistent sets are Hinziker, and from that immediately you got model existence. So this is kind of a very abstract version of model existence. Yeah. Okay, so here's one application, bounded first order logic. So imagine you have a first order logic with this kind of rule. Namely, you can take a universal quantification and then you can instantiate it, but only to subterms of gamma. And this is actually enough for completeness. You kind of only need to instantiate to things that are relevant, you can say. Yes. So then you can see in our framework for the alpha rule, we actually allow for you to specify both what instances do you want, and well, how do you actually construct an instance. We also have a second order logic, and here you can see we have 3 kinds of universal quantifications: one for terms, one for predicates, and one for functions. So you can see that the definition of gamma we have defined is quite flexible. And then lastly, we have a very recent modal logic. So Asta managed to formalize completeness for a very recent modal logic by Blackburn, Breuner, and Kofod. And this is also kind of cool because it's really formalizing, research fresh out of the press. Yeah. So let's try to conclude on this talk. So consistency properties, they you can build maximal consistent sets from them. And in our framework, the kind of key insight is this this slicing of respectively properties for consistency and being Hintika. And then if you want to use our framework, then you can actually use the definition of alpha, beta, gamma, delta that we already did. But if you have some funny construction that's special for your logic, then you can focus on how do I formalize that one and not focus on the usual things. And you also don't need to think so much about how to construct the maximal set, because the framework can do it for you. So my hope is that you will prove model existence and completeness for a lot of cool logics, and that you will use our fantastic framework for doing this. Thank you very much.